Alrighty, so PEMDAS. We just left off in the other video, kind of explaining how to go about using time to go ahead and discuss why PEMDAS is the order of operations. And specifically, I'm going to be talking about the stuff that comes after parentheses, because like I was saying in the previous video, parentheses is just a marker of priority, and so it's kind of a way to tell the audience, hey, just do this first if you are a writer of mathematics. And so that is the reason parentheses is at top, because it kind of gives the writer the ability to say, hey, regardless of what you would naturally do, follow the parentheses first, and you will get, you will understand what I'm wanting to happen first in this scenario. Because sometimes you really do want to, for instance, add two of something to a collection. Like if you add two apples to a basket before you distribute the basket to your friends, that'll change the problem if you just distribute it first and then add two apples to something. I don't know. It just, you might, and sometimes in life, want to do addition or subtraction before you want to do anything else. Parentheses help you to be able to do that. All right, so I'm going to start off where you start off in learning math and generally speaking, with addition. So addition, subtraction, 4 minus 2 minus, or 4 plus 2 minus 3, plus 6 as well. I'm going to go ahead and just talk about what this is. So addition and subtraction is essentially just movements along a number line. You can imagine there's like an implicit 0 here. If I were to add 4, so a positive 4, you can also imagine I start at 4. So I travel 4 away. If I were then to add 2 to this, I would move maybe half as far, like that, boom, and I'd wind up at 6. If I then subtract 3, I move back 3, maybe I end up around here, which will be at the number 3, and then I can add 6, and I wind up, should be at 9, so boom and boom. I'll extend my line here, I'll get rid of that arrow for a second. Okay, smooth, okay, perfect. Pull this down, and this will be at 9. That's where we end up if we do this subtraction addition from left to right. If we did it in any other order, you can imagine I did this negative 3 first. Well, negative 3 is over here, so I can imagine I start off by subtracting 3. Let's say I then choose to add 2. I go back to around negative 1, and then I say, okay, I'm going to add 6 next. Well, 6 would take me to positive 5. So imagine I go over to here, it's like right there, positive 5, and then I add 4. Hey, look at that, I'm just traveling this way here. So you think of addition, subtraction, just movement along a number line, or it's kind of like you average out the length of arrows and the direction of arrows, and you should wind up in the same spot no matter what, because while I'm moving left a little bit and then I'm moving right, the overall movement right is 4, 2, and 6, and the overall movement left is minus 3. So I can move right and then left. I can move right, left, right, left, right, left, right, whatever amount that I can specified by the given expression. However, it's just moving right and left, and those are kind of independent of one another, and you can sum up all of the right hand movements, all of the left hand movements along the number line here, and you should wind up at the same spot. And so that's why we kind of say addition, subtraction, they're kind of like two sides of the same coin. They have the same priority level. You do them in any order you wish, and you kind of get to the same destination, which is in this case 9. So that's just about addition and subtraction. I will then talk about the multiplication, division, kind of explain why they're the same priority level. Oftentimes division is kind of been touted as the opposite of multiplication, the same way that addition and subtraction seem to work as opposites a second ago. So opposites, let me just, opposite. And I can also think of it as like undoing multiplication, division does. However, I'm going to go ahead and write out a few problems and see if this makes sense to you. 4 divided by 2 is just 2. 4 over 2 is just, well, 2 over 1, which is just 2. And also, 4 over 2 is also equal to 4 over 1 times 1 over 2, which of course is just equal to 4 times 1/2. So hopefully all three of these equations kind of make, all these little equalities here make sense to you. I say, okay, 4 divided by 2, that's a division fact. It's kind of like what number times 2 is equal to 4? Well, 2. This is saying, okay, this is a fraction, 4 over 2. Hopefully you've learned to reduce it, and it gets to 2 over 1. Well, 2 divided by anything is just 2, or 2 over 1 is just 2. Division and fractions are almost synonymous, or pretty much synonymous here. And then here, this 4 divided by 2, I could kind of imagine this as the result of a multiplication of two fractions, 4 over 1 and 1 over 2. If you multiply these together, straight across, 4 times 1, 1 times 2, you get 2 and 4. And then 4 over 1 is the same like up here. It should just be equal to 4. And so ultimately, we see that while, of course, 1/2 is like a little division here, I could imagine I write that guy as 4 times 0.5. Division ultimately is nothing but multiplication, just using numbers that are not integers oftentimes. So for instance, here it's 4 times 1/2, so it's kind of like just an extended version of multiplication of integers. So that's kind of why division and multiplication are in the same ledge, or at the same level here, because, well, they are essentially doing the same thing. It's just, the types of numbers you're working with are a little bit extended in order to reach that. You have to extend the domain, or the numbers that you're working with, to include things like fractions and whatnot before you can kind of just understand, multiplication, division, same kind of thing. All right, so that's why each of these are paired together. Let's talk about why multiplication division is above addition and subtraction. And to do this, I'm going to just wrap our heads around why multiplication is higher than addition. So if you think about what multiplication is nothing but repeated addition. So right here I have 4 times 4. 4 times 4 is nothing but 4 times. So I'm going to write it in words. This is 4 times, that's meant to be a comma, 4, 4 times, because we're going to add 4 to itself, or add 4 copies of 4 together, and that's what multiplication is set to mean. I'm going to change it to be 5. Maybe I can say, okay, we have 4 5 times. Leave it like that. I wrote a 5 there. I'm dumb. I was talking and saying 5, and boom. So yeah, all 5 of them together, you'll get 4 5 times. And we see that if we were to write an expression here, if I were to write 4 plus 4 plus 4, let's say plus 3 minus 2 plus 6, this expression, I could say 4 plus 4 plus 4, well, that's just 12. Well, it's also 4 3 times. Now I'm going to also keep track of this being a 12 right here. I'm going to say, well, 3 minus 2, that's a plus 1, and then plus 6, of course, is just there. So I say, okay, what's 12 plus 1? That's 13, plus 6 is 19. Now, if I treat this as 4 times 3, well, 4 times 3 is also 12, so I really didn't do anything different there. And of course, I can still add 3, and I can subtract 2, and add 6. And if I did it according to PEMDAS with multiplication ahead of the addition, then of course I can do this guy first. I get 12, and then I add on the rest of this like I otherwise would. However, the way to figure out why we do multiplication ahead of addition subtraction is by experimenting. Well, what if we don't assume this is true? What if we assume that it's false, that we must do addition or subtraction first? And we can also say, what if addition and multiplication are on the same level? Maybe there's 4 things on the same level instead of just 2. I'm going to explore both of those right now. First, let's assume that multiplication is a lower priority than addition and subtraction. Well, then I have, okay, 4 times 3 is going to be last. So I'm going to do the addition first. I'm going to say 4 times, 3 plus 3 is just 6, minus 2 plus 6. And then I still can't do the multiplication because I have now addition and subtraction here. So I got to do those first. So 6 minus 2 is 4. And then I have 6 plus 6, which is 12. So I have 4 times 12, which now I can finally do it. It's 48. However, we got this expression from here, and we made sense of that because, well, this is just saying 4 3 times, or 4 plus 4 plus 4, and that's how we define multiplication to begin with. However, this jump, where we then treat addition as a higher priority, led us to 48. In our initial answer here, when we're just adding, subtracting, which are known to be equal priority, gives us 19. So if we say multiplication is not a higher priority, or if we say multiplication is a lower priority, if we say this is wrong up here, we get two different answers for the same expression, which, that expression should only be equal to one individual thing. So that kind of tells us that no, what we just did is bad, bad, bad. It is not the case then that multiplication is a lower priority than addition. However, what if it's the same priority? Well, hopefully you're going to see where I'm going with this. Maybe we can do it in whatever order we want. Well, if that was the case, well, actually, I'm going to bring this back. Then it should be the case that I'm allowed to do the addition first here, because it's same priority, and then I'm allowed to do the subtraction there. I'm sorry, I think I might have done that incorrectly. 6, 12, it should be 10, but either way, I think that should still be, so 6 minus 2 is 4 plus 4. It should still be 40, but that's still different than 19. But the same thing would work if they're the same level of priority. I could just keep choosing to do the addition and subtraction, then, in which case I still get 40 here, or maybe I get some other answer depending on when exactly I choose to multiply. But yeah, multiplication clearly must be ahead of addition, because if it's not, well, the other option is either equal or it's less than in terms of priority, and either of those can lead me to the answer where I get 40 and 19 for the same expression up here. So that explains why this part of the hierarchy exists: multiplication, division over subtraction and addition. Now we're going to explore exponents. So the first thing I did when I explained or talked about this multiplication and addition subtraction gap is I said, okay, what are exponents? Or sorry, I was talking about what is multiplication really? Well, here now I'm going to talk about a little bit what exactly are exponents, or how should we treat the exponents. Well, if I were to write, for instance, 3 to the third power, this says 3 copies of 3 multiplied together. So 1 copy, 2 copies, 3 copies multiplied together. In this case, that would equal to 27. Hopefully this makes sense. And if I were to say 4 copies, this would be 3 to the fourth power. You would see that I indeed would say 3 times 3 times 3 times 3. And this would then be 81 instead. 81. So why are exponents a higher level priority? Well, let's go and visit this. Imagine we had an expression like 2 times 2 times 2 times 2 times 2 times 5 times 7, for instance. And I wanted to say, okay, well, what is this? Well, 2 times 2 times 2 times 2, I don't know why I did that. This guy right here will come out to be 32. It would also be 2 to the fifth, as I was saying before, because we have 5 copies of 2 multiplied together. Now, cool. Being 2 to the fifth, I can then make a substitution there. I can leave it as 2 to the fifth and have a times 5 times 7. Now, 5 times 7 is 35. And, if I were to take 35 and multiply it with 32, well, I would get, let's see, okay, so we'd have 70 plus we'd have, what is that, 905? 105, although it would be 1050, 1050, which should be 1,000, 1,200 and 1,120. Oh my gosh, I am a mess. 1,120. Yes, cool. So 1,120 should be our answer here. 1120. I'm gonna move this to the side. That was my little math on the side. I didn't feel like trying in my head because I got it wrong. Then I have this, which if we do 2 to the fifth first, I should get 32. and then multiply by this, which is 35, I should get the exact same result because I would be doing the exact same thing. However, let's imagine now that multiplication was higher or the same priority level as exponents. So I'm actually going to move these on the other side just so it looks in the form that another student of mine might mistake. So here, and I say that because like if you have numbers on the out on this side of it, if I have like times 6, normally students might remember seeing parentheses at some point, and then you do what's on the parentheses. I feel like it's a little bit harder to make the reach that this exponent applies to the 6 because the 6 comes after it. However, when the exponent comes after the multiplication, it might look a little bit more muddied. Well, is this fifth power kind of applying to everything? I don't know. And here we have multiplication coming before, like in terms of like left to right, it comes before the exponent does, and so students might get confused. Well, need not to worry. Let's go ahead and just test out what would happen. So let's imagine that we did multiplication first, or that we could do multiplication or the exponent at any given time. Well, then I could say, okay, 7 times 2, that's 14. I'm going to keep this exponent here. I don't have to do it yet, according to our little assumption here, our little game we're playing. Well, I could then either stop there and say 14 to the 5th power, which is, I don't even want to compute that, or I could continue and see, okay, now we have 70 to the 5th power, and my goodness, that looks like a big number. It would be 70 times 70, which would be, 4,900, times 70, and this is already getting massive, and hopefully it's already more massive. So I've done 2 copies of 70 multiplied together. So this is 70 squared, and we see that 4,900 is already bigger than what we had there. Imagine if I were to then multiply it by 70 squared again, and then times 70 one more time. That would be a gigantic number, and way, way, way bigger than what we initially had, which was 1120. And hopefully I did that math right. However, either way, the numbers are clearly very distinct. And so that tells us, well, if we make the step, if we draw the conclusion that we might be able to treat exponents as either less than or equal priority to the exponent, then we get a wild answer down here, which goes against what we would expect. And so that explains why exponents are higher than multiplication. And because multiplication is higher than addition, we say exponents are likewise higher than addition. That's a little transitive property. If one thing is ahead of one, or one thing is ahead of another, and that other thing is ahead of something else, then the first thing is higher than the third. That made sense to you, fantastic. But yeah, that's essentially explaining why at least these guys are in the order that they are. And then a reminder from the previous video, parentheses are at the top because it's kind of like an author's note. So if I were to be the one writing this mathematics and I actually wanted to do the multiplication here first, maybe I wanted this I had 5 of these and 7 of something else and 2 of some other third thing, and I wanted to get a sense of how many copies I can make of all of it. Well, I could maybe choose to do the multiplication first and then raise it to whatever power that I need. And if I wanted to do that, I would need parentheses to mark, hey, do this multiplication first. And yeah,